Okay, so picking up where we left off last time, we were talking about parametrizing surfaces, and remember, this is not an algorithmic process. There's various different ways. Think of it as tools in your toolbox, and so here we go with yet another tool. So roughly speaking, the idea of this one is to create a whole new tailored coordinate system for your surface, and then use that to create a parameterization. Let me just show you an example of how this tends to go down. So we're going to apply this idea to a torus. Torus is the surface of a donut, something like this. Okay? And notice the particulars here, that the big radius, I guess you might call it, is A, and then the small radius, you might call it, there is B. Okay, so here's what I'm going to call a good choice of a new coordinate system. I emphasize this is a choice. This is not the only way to do it. There are many other ways to do it. I think it's going to be hard to beat this one. There's many others that are equivalent. Okay, so the idea is as follows. Let's pick and I'm going to zoom in so I can see better. Let's pick, and let's also do this move. Okay, there we go. Let's pick a single point. I'm going to pick this point right there as what I'm going to call our starting point. And I'm going to describe the location of some arbitrary other point, like that one in purple, in terms of the following two coordinates. Big idea is I want to keep track of how far I have to sort of rotate upward to get onto sort of the same level as the purple point, and then how far do I need to rotate around to actually then get to that purple point. And now, geometric appeal, no matter what point you're looking at, no matter what purple point you're looking at, you can get there from your base point, from your starting point that I have in dark blue here, by just rotating by some angle T, and then by rotating by some angle S. Everybody see my coordinate system? It's sort of like longitude and latitude, approximately. If you were to make a longitude and latitude for a weird shaped planet that's shaped like a donut, right? This would be kind of longitude and latitude. Is everybody on board? Okay. Now, I emphasize, this is not the only way to do it. I think this is a reasonable natural choice, though. And notice further, this is not like some rule that you should always do. This is tailored to this particular surface, right? It's because the donut is kind of, if you will, round kind of in this way, and also kind of round sort of in that way. And so I made my coordinate system kind of work with sort of the fundamental geometry of my shape. All right, so what? How does this create a parameterization? Well, remember, a parameterization is where you solve for x, y, and z as functions of two parameters. I'm just going to let S and T be my parameters. All I have to do then is solve for x, y, and z of my purple point in terms of S and T. All right, now there's a significant amount of geometry to be done here, and again, different ways that you can go about doing that. I'm going to show you what I think is the most direct little bit of geometry here. I'm going to let y'all follow through the details. There's a fair amount of vector geometry, vector algebra, trig, and a little bit of linear algebra involved in this. All that's prerequisite, all that stuff that y'all can do. But nevertheless, rubber meets the road. Make sure you can actually do that. Big idea is, let's see here. Oh gosh. Okay, so yeah, so I'm going to notice that vector right there is easy to write down. I'm going to notice that this vector right here is easy to write down. And a little bit of trig in that, a little bit of geometry. Think it through. Make sure you can persuade yourself. Yep. And then I'm going to notice that the sum of those is that point P. That's my first, sort of the first half of the argument. Details to be filled in by y'all. And then the second observation to make is that once I have the coordinates of that point in red, that point P, all I have to do to P to produce the point that I'm actually interested in, and keep in mind my goal is to understand this point X over here, all I have to do to turn P into X is rotate it, right? So I'm going to then ask, how do I rotate by an angle S around the Z-axis? Linear algebra kicks in, right? Now again, make sure you can do this, but old linear algebra arguments, we reviewed in chapter 1, and reviewing from Math219. This is the matrix that will do a rotation around the Z-axis by angle S. Make sure you can do that. If you're not comfortable with it, if you don't know where this came from, if you don't think you can do this, come to office hours. Very happy to help, right? Let me help you, right? But you got to come to office hours for me to be able to help you with that. So that's the rotation, and so you just do that rotation to that point P that we just wrote as a sum of vectors, and sure enough, that gives you position. That gives you X, Y, Z. Wrong color. That gives you X, Y, Z. Notice it is as functions of S and T, and that is a parameterization of that torus. Okay, so big picture. Now, a lot of little details. Don't get lost in the details. The big picture is create a coordinate system. Make a decision on how would you describe, what's the easiest way that you can think of to describe location on your surface. Tailor your coordinate system to your surface, right? And then just solve for position. Solve for X, Y, and Z in terms of those coordinates. And you've got yourself a parameterization. So it's a really, really useful method. Lots of situations where this is the best way to parameterize. Okay. Moving along. Sometimes the thing you want to parameterize is very similar to something that you've already parameterized. And so when that happens, when you're trying to parameterize something that's really close to what you already have, tweak it. Right, and just tweak it appropriately. So here's a little example of that in action. We already know how to parameterize the unit sphere. Unit sphere. Keep in mind the unit sphere has a really simple spherical equation, and I want to remind y'all, last time I think it was, we talked about the graph parameterization, and in particular you can do that in any coordinate system, and we did an example of a spherical graph parameterization. Right? And if you do that, that will produce this parameterization of the unit sphere. Which, by the way, of course, keep in mind, these are literally X, Y, Z. Right? And so that parameterization you can rewrite as 3 separate equations. Okay. So that's a parameterization we have. A reminder, we got it from the fact that this is really easy to write in spherical coordinates, and spherical coordinates in this case is just super convenient. Okay. All right, so what if, though, instead of the unit sphere, instead of the unit sphere with that equation, what if I want to parameterize an ellipsoid which has that equation? Now, is this easy to write in spherical coordinates? No. It's really hard to write, and I don't even know if it's practical to write this in spherical coordinates. It's really not on the table, right? So I can't use a spherical graph parameterization. I can't use a rectangular graph parameterization because this is not a graph. Fails the vertical line test in all 3 directions. Okay, what I can do, though, is notice that it is pretty algebraically similar, and in fact, it is literally just a stretch. Three different stretches, I guess, right? We're stretching by a factor of A in the X direction, by B in the Y direction, C in the Z direction, right? This is just a stretched out version of our sphere. Is that cool? So we can actually use that observation, and again, this is a callback to chapter 2, right? Remember in chapter 2 we talked about how algebraic sort of, replacements like this result geometrically in stretches. And, okay, how do I use that observation to edit the parameterization? Well, this parameterization I can turn, by the way, of the sphere, I can turn into this parameterization of my ellipsoid by doing the same stretch. Just everywhere you see x, replace it with x over a. And I mean, after all, this parameterization is made up of 3 different equations. All the same rules apply, and if everywhere I see an x, I put x over a, that accomplishes this same stretch. And notice that's pretty much giving us a parameterization, because this, you can solve for x, y, and z, and then you can lump those together, and there's a parameterization of our ellipsoid. Everybody see what happened there? So these little tweaks are nice. Now here's a different take on it, a different way to think about it. You will notice that the formulas we have for x, y, and z in our initial parameterization, those expressions show up pretty prominently in our new parameterization. Right? So a different way to think about what has happened here is that I have taken my literal formulas for x, y, and z. Here they are, my literal formulas for x, y, and z. And I'm stretching them by just literally making them bigger by the appropriate factor, right? The formula for x, well, I want to stretch by a factor of a. Okay, well, those x's are going to be a times as big, and those y's are going to be b times as big, and likewise the z's c times as big. So you could just kind of do it in some sense, but I kind of like discovering that that is allowable by seeing that it results from something that we already knew how to do. Okay, is that satisfying? All right. Okay, moving along. A quick comment. The book does give several more examples. There is something that's qualitatively different about all of the book's examples. All of the book's examples start with an existing parameterization. Given. Here's a parameterization. And then what they do is they kind of argue backwards. They say, okay, well, given this parameterization, let's figure out what the underlying surface is that it parameterizes. Right? All of my examples go the other way. All of my examples say, here's some surface. How do we create the parameterization? Right? Now, I chose my examples to go my way for 2 reasons. First of all, it's to complement what's already in the book. Right? You already have the book's examples. Also, frankly, I think my examples are going to be more useful to y'all in the long run, because in my experience, most of the time, when you need a parameterization, it does not come given. Most of the time, like if you need to do something with a parameterization of a sphere, all you're going to know starting out is, okay, here's a sphere. And you're going to need to be able to create the parameterization, right? So I showed you these examples so that you'll have the tools for being able to do that. None of the book's examples actually show you how to create parameterization. So a little this, a little that. Okay. All right. Now this next page is one of these tough choices that I have to make. I'm going to skip over this page. In fact, you could, I don't want to endorse the following statement, right? But you can kind of get away with not looking at this page, I suppose. I don't advise that. I do hope you all will read this. I think it's pretty readable. This is supplementary, by the way, to what is in the book, right? So you can read the book as well. I think there's good ideas in here, and ultimately what I have on this page will help you understand what we're about to do next. But this, I don't think, quite makes the cut for being worth class time. So I'm going to skip over that. Most of that we won't really quite do anything with. And I'm going to go right to this page right here and just kind of pick up. So you'll notice we have here a parameterization. This is the picture, anyway, of a parameterization of a sphere. And position on the sphere is a function of parameters, phi and theta. And you can see that if you were to move from some input point in the phi direction, let's just think about, well, what happens on your sphere if you're moving in the phi direction, so theta stays constant, we're going to move in the phi direction. Think about how spherical coordinates works. Moving in the phi direction would have you going basically south on the sphere. And okay, well, alternatively, you could move in the theta direction, keeping phi constant. And again, think about how spherical coordinates works and what does that mean? And well, that would have you move like that. East, in other words. Yeah.
Could you please explain again the number?
Well, yeah. So keep in mind what phi and theta are, right? So theta is this way,
Yeah.
right? And then phi is kind of like that, right? So in this green direction, you see theta is not changing, right? But I'm going in the phi direction, so phi is increasing. So that means that I'm at a certain point, and my theta is not going to change, but phi is going to increase, and that has me going south. Yeah. Okay, so I propose then that this little piece of area, now this represents a little piece of area in the phi theta plane, gives rise then to this little piece of area that I'm going to call ds on the sphere. And y'all have seen a situation like this many times, right? So we have an input space and an output space, and we've got a function that goes from the inputs to the outputs, and we've got little areas here and we've got little areas there, or maybe volumes here and volumes there, various different versions of input size and output size. And the natural next thing you can probably see coming is we're going to want to relate, by what factor does this have to get stretched in producing that, right? So we want to figure out what is our stretching factor. How much bigger is this little red area on the sphere than this little orange area in the parameter plane? Okay. So I'm just going to assert what that answer is. The answer is that output area relates to input area by a stretching factor that is this formula right here. I'm going to do a rough hand wave to this. Y'all can see that this little piece of area, this little output piece of area, is a parallelogram-ish. Right? It's approximately a parallelogram. In 3 dimensions, what's our formula for computing areas of parallelograms in 3 dimensions? It's the magnitude of a cross product. Right? And so hopefully no surprise that the stretching factor here is a magnitude of a cross product. And in particular, these x phi and x theta, and let me just go to my little summary page down here. I'll go back in just a moment. But those are partial derivatives, and those are going to be tangent to the surface. Now, I did gloss over why that is. If you want to see, if you're not comfortable with my claim that these are tangent vectors to the surface, you can look at that page that I kind of skipped over, right? You can come talk to me in office hours, of course. But anyway, I'm going to claim here that they are, and again, feel free to talk to me, or feel free to look at that page, or feel free to look. By the way, another little trick y'all can do, I hope this is a useful observation. If I ever gloss over something a little faster than you would have liked, this semester, I've got years of old videos on my YouTube channel. You can click back to last year and see how I treated that last year. I might have given a more detailed discussion. You never know, right? So feel free to look at old videos, whatever is most convenient. Okay, so yeah, here is our stretching factor formula, and let me clean up the mess I got going here. I'm just going to erase everything and start fresh. The stretching factor formula that turns input area into output area is that. Okay, now you'll notice that the vector whose magnitude does this is a cross product. Cross products are always perpendicular to the two inputs. These two inputs are tangent vectors. I hope it's no surprise that the cross product is perpendicular then to the surface. Right? You get two vectors parallel to the surface, their cross products perpendicular to the surface. So we call this a normal vector, and we're going to give it a more careful. Actually, let me work my way around here. We're going to give this a notation and a more careful name in a moment. The notation, we're going to call that capital N. So I don't want to go so far as to call it a standard, but it's a very common notation to represent this cross product of those partials. It's used for a lot of different things, one of which is just as a shorthand. It is a single vector whose magnitude is that stretching factor, and so instead of writing this formula, magnitude of the cross product of the partials of, it's a lot easier to just say magnitude of capital N. Okay. Is everybody with me? Okay, let's talk about the name. This is a normal vector, right? We talked about that. It's a cross product of tangent vectors, so it's a normal vector. I like to call it the parametrized normal vector. I think this is a good choice to call it the parametrized normal vector because of the following, I think, really important observation. This vector depends on the parameterization. Right? You can see it right there in the formula. Right? X is the parameterization. X is the thing whose partials you have to take and then subsequently cross to produce N. So different parameterization, different capital N. That make sense? Now they're all perpendicular to the surface. But depending on what your parameterization is, your capital N might be longer or shorter or possibly backwards, right? Pointing inward instead of outward or whatever. It's a bunch of different possibilities. And so this capital N depends on the parameterization. And given that it depends on the parameterization, I like to call it the parametrized normal vector. Okay, so that's the terminology I like to use. Now, you'll notice I put here in faint print, recognizing what the book calls it. The book calls this the standard normal vector. Words are arbitrary, I suppose. You can call it that. I find this term confusing because standard to me, right, to my ears, when you say standard normal vector, that makes it sound like you're talking about something that's intrinsic to the surface. I mean, it's the standard, right? It makes it sound like that's the one. And as we just observed, it depends on your parameterization. There's lots of parameterizations. There are lots of capital N vectors. I think it's weird to call them all standard. You know what I mean? Now, I'm sure the counterpoint on that would be, yeah, they're standard to the parameterization, but it doesn't come across if you just use the term standard normal vector. That's my beef with that. Anyway, I'm going to use the term parameterized normal vector. Okay. All right. So let's see here. Well, let's do something with this. I can get this to cooperate. I'm just going to erase like so. What I would like to do is let's compute the area of this sphere. Oh, and let me there we go. We're going to compute this area of this entire sphere. Okay. y'all already know the answer, right? This old high school geometry thing. You probably even computed this area previously. There's a point of view on single variable calculus where you can take slices and make a bunch of onion rings, right? And then argue that the area of each onion ring is, blah, blah, and add them up with a single variable integral. That works. That's fine. No problem. I'm going to show you how to do it with an argument that is kind of going to be a little bit of a precursor to a general construction called a surface integral. So the purpose here is not to get the answer. The purpose is to sort of suggest a new idea. Right? Okay, so the big strategy on this is to notice that the total area is the sum of a bunch of little pieces of area, all these DS's. We're just going to add up all these DS's. We're going to do that for all of the allowable values of phi and theta. Right? Theta is going to go from 0 to 2 pi. Phi is going to go from 0 to pi because that traces out the those are the values of phi and theta that will make the entire sphere. And so if I know those dark green areas, and if I can relate them to these dark blue areas, I'm just going to be viewing these as stretched by a factor versions of these, and then add up with an integral in the phi theta plane. It's kind of a pullback. It's kind of like other pullbacks that we've done previously. It's that now we're pulling back from a surface instead of pulling back from a different coordinate plane. Everybody see the big picture? All right, so in order to be able to do that, we need to know what that stretching factor is. In fact, wait a second, in order to be able to do that, we need to know what the parameterization is in the first place. So we need to parameterize our sphere, then compute the stretching factor, and then it's just a matter of writing down the pullback. Okay, so here's where I'm going to leave a lot of this for y'all to check details, as is often the case. So this is the parameterization we're going to use. This is something we wrote down previously. This is the spherical graph parameterization of the unit sphere. This comes out of rho equals 1. Make sure you can do that. Make sure you can make the argument that turns rho equals 1 into this, right? Reminder, we did an example very much like that in a couple pages ago. That would have been on Friday when we talked about the spherical graph parameterization. So you want to fill in those blanks. Next, following our formula up here, our stretching factor. Oh, whoops. Our stretching factor is just the magnitude of our capital N. Our capital N is a cross product. It's a cross product of the partials, specifically the partials of our parameterization, right? So several step process. We're going to take the parameterization we just wrote down. We're going to compute those partials. We're going to take that cross product, and then we're going to take its magnitude. And when I say we, I mean you. So good blanks to fill in. Those are the partials. Here's how the cross product works out. I know it's a lot of trig, right? That's the way a lot of stuff works, right? So make sure you can fill in these blanks. It's a lot of trig to make sure you don't get bogged down. Make sure you know all the appropriate identities and symmetries and properties of trig necessary to make this work. And then we compute the magnitude of that. And it works out really nicely. It's shocking even how compact and convenient that answer is, that the stretching factor is just sine phi, given how ugly this capital N vector is. Right? It's weird that it simplifies that much. Pythagorean identity kicks in several times in doing that, in doing this last, the purple calculation here. Several instances of Pythagorean identity. So healthy exercise, go through, please. Make sure you can do that. Make sure you get the right answer. And now it's kind of all over, but the shouting. Keeping in mind, we were going to compute the total area as the sum of a bunch of these little pieces of area. Those little pieces of area are stretching factor times the parameter space areas, previously argued. Let's see here. Let's see here. The stretching factor we just computed. Stretching factor is sine phi. And so this turns into actually a really easy little double integral, and y'all can totally do that, and that gives you the total, which is 4 pi. How we doing? Okay, so make sure you can do that. Again, office hours, if you have any questions, don't hesitate to come ask. I'm happy to help. And back to this little summary page. There's this is just kind of bringing it all together for convenient reference. This is a good page to flash back to periodically. We're going to be doing a lot of stuff with surfaces, and again, several of the players involved in this little story that we just dealt with are here. So we have the parameterization, the various partials, right, with respect to your two parameters, the parametrized normal, which, by the way, keep in mind, the parametrized normal is in the direction of a unit vector. We're going to make reference to this parametrized unit normal vector at some point in the future, probably Wednesday. So keep a lookout for that guy. Little n, that's just a unit vector pointing in the direction of capital N. And of course, its magnitude is the stretching factor for the areas, as it turns out. All right, now the last little bit that I have on this page is just kind of cultural reference. But you can take this formula for capital N, you can write it out in coordinates. Nothing happened here. I just took the x vector and wrote it out as x, y, z for each of those partials. I'm just writing it out in coordinates. And then, again, nothing happened here quite. I just multiplied out the cross product. What is weird and unexpected is that the individual coordinates, when you do that cross product, very surprising, but those individual coordinates end up being two-dimensional change of variables stretching factors. Do the algebra, write it down. Son of a gun, it works. Very surprising. It's what I like to call an eyebrow raiser, right? That's suspicious that maybe there's a good reason for that. So again, as a cultural point, I think it's good to know that this is actually not a coincidence. There's a really good reason why these are seemingly coincidentally two-dimensional change of variables stretching factors. And it's very unfortunate that we don't have the 15 minutes or so that would take me to explain here in class why these are two-dimensional change of variables stretching factors. There's a really good reason for it. It's very geometrically natural. It's really interesting. It's a fun discussion. I'm sad I can't tell you, right? But if you're curious, come on into office hours. I'll be very happy to show you. It's a fun conversation. But anyway, you don't have to know. It's technically not part of Math219 material. Okay. All right. Lovely little special case. I emphasize this is a special case. This is not an alternative, substitute alternative, right? If you don't like the parameterization technique, that is absolutely not the case. This is a special case. It only works if you're looking at a graph. as you see we are right there, looking at z equals f of x comma y. And furthermore, it only works if you are specifically using the graph parameterization. And I'll remind you, this is what our surface graph parameterization formula looks like. Remember, the big idea of graph parameterizations is you let your input variables x and y be your parameters s and t. That's the deal. And then z does what it has to do. Okay, so special case, if you're looking at a graph, if you're choosing the graph parameterization, the nice things happen, because the partial derivative, wrong color. The partial derivatives will always look exactly like that. The cross product will always look exactly like this. The magnitude will always then be computed by that formula. And you can just memorize that formula. Right? So very convenient. And by the way, even though it's a special case, yeah, but it's a really common special case. Graph parameterizations are awesome. They come up a lot. So rather than, in this, again, fairly common scenario, rather than writing down the parameterization, doing the partial derivatives, taking the cross product, computing the magnitude, and rather than going through all of that and subjecting yourself to the potential for making mistakes and costing you time that's critical on a test, etc., just write down the formula and go from there. Right? It's a nice trick, and you should definitely know that formula and use it appropriately. Okay, nice little special case. But again, special case, not everything's a graph. In which case, this formula is garbage. And hey, even when that stuff is a graph, you might not want to use the graph parameterization. Sometimes there are much better choices. In which case, that formula is garbage. Right? So, to be used sometimes. All right, last little observation I'm going to make on this formula is, now this is just noticing, but this expression right there is the square of the magnitude of the gradient. Chapter 2 reference. Oh, wait a second. Furthermore, the magnitude of the gradient is the steepness of the graph. Okay, well, so that's actually pretty neat. What that tells me is that in this case, your stretching factor depends only on how steep is your graph. And beautiful little conclusion. If you know how steep your graph is, you don't have to do any of these calculations. If you know how steep your graph is, I'm going to show you an example in just a moment. If you know how steep the graph is, boom, done. You don't even have to write down equations. Everybody on board with that? Okay. So here's the example I'm going to show you. This is very real world. Suppose you are going to put a roof on your house, which, by the way, if you ever buy a house, sometimes you have to put a roof on it. Well, one of the determinants of how much it's going to cost, which may matter to you at some point, how much it's going to cost to put a roof on your house is what's the area of your roof. And just for fun, let's kind of ooh and ah over how difficult of a little high school geometry problem this would be. It's made up of parallelograms and triangles and various weird shapes. So none of those angles are right angles. So I guess you could do it, right? But it's kind of inconvenient. By the way, there's the related question of measurement, right? How are you going to figure out what that length is? Are you going to climb up to the top of your roof with a tape measure? I hope you don't fall, right? I had to climb up to, I was cleaning out my gutters one time, and 2-story house, and I'm on a 20-foot ladder, and I got to let you know, I was scared, right? That is a scary experience, and it occurred to me, there is concrete below me. If this ladder buckles, right, then I hope I die. Because right, because I don't want to be mangled for the rest of my life, right? It's scary experience. So I just got down off the ladder. I didn't do it. It's too scary. So I guess you can climb up to the top of your roof, but I don't think that's a good idea. So I want to show you a much better idea, right? If you need to compute this surface area, notice that roof is a graph. It's a graph which you could view from a point of view of a graph parameterization above the footprint. The footprint area is easy to calculate. You're measuring while you're standing on the ground, nice and safe, right? All these angles right here, right angles, right? Easy measurements, easy geometry. No problem to compute that area. Nothing to it. Okay. All right, so how am I going to relate this area to that area? Well, the beautiful observation, and this is just how it turns out, but your stretching factor here that turns input areas into output areas. That stretching factor depends on steepness and a little oddity of housing design, I guess, is that if you look at a rafter on a house like that, the slope of the rafter, the steepness of the rafters, those are approximately constant. They're pretty much constant on any given house. And there are exceptions. Sometimes architects get creative and they, interesting things, and it, not true on some houses. But on, I think every house in my neighborhood, constant. Right? Yes.
So how would you get it without climbing up?
Yeah, you go into your attic, which is good enough. Yeah. You go into your attic and you can the rafters are just right there. And yeah, so what I did is I got a yardstick and I tacked it up to a rafter, and it hangs down. Gravity makes that nice and vertical for me, right? And then I take another yardstick and hold it with a level, and make sure that it's nice and level, and just you measure the rise and the run, and it's very doable. Yeah. Nice and safe in the attic. Yeah. So anyway, the point is you can measure that steepness. Once you know that steepness, then you know your stretching factor. Because of the fact that steepness is constant, your stretching factor is constant, and it'll factor right outside of your integral. And look how easy that calculation is, and you don't have to get on the roof. You don't have to do a bunch of geometry. You don't have to measure a bunch of. What are you gonna again with I guess you could have a protractor up there and measure that angle, right? But so much easier to just do this little calculation right here. Now, should you bother with this at all? It's up to you. You don't have to. You can trust the guy that's going to charge you 5 figures for your roof. You can just trust that he's going to do that calculation correctly, right? I don't. I tend not to trust when there's big money involved. I think it's worth a double check. And for whatever it's worth, I've done a lot of double checking of calculations and costs in my adult years, and I have caught many mistakes. Now, shocker, all the mistakes that I've caught were in the favor of the other party, right? I've never accidentally been undercharged, right? And I've saved myself something like $6,000 by just paying attention, right? Double check. Don't trust them, right? I'm sure it's inadvertent, right? But anyway, this is a worthwhile. And this is an easy one, right? Super easy to do. So, all right. So, fun example. Okay, moving along. So we've talked about how to compute a surface area, a couple of examples of surface areas, and this is a special case of a more general construction called a surface integral. I'm going to quickly here, let's see here, let me hit that button, and then I have to hit this button, and then that, but there we go. Okay, so y'all will recall, and I'm doing this just for analogy purposes. I know the print is too small to read in the back, so I'll magnify it again in a minute. But you remember at the start of chapter 6, we talked about what does it mean to do an integral on a curve, right? And conceptually, yeah, the whole is the sum of the parts. Chop it up, add it up, right? It's not a deep idea. It's the same idea of every other integral we've ever done. If you want to, compute the mass of a bent wire, or if you want to know how much snow is there on your curved driveway, maybe you've got a really long, windy driveway out in the woods, like I did one time. No more, but anyway. You're going to add that up by breaking it into little pieces. On each little piece, the calculation is easy, and then you add up over the whole, right? And we defined this thing called a scalar line integral. It's largely just notation, but the big idea is on each piece you talk about stuff per unit length times length. You write down a new kind of integral. Now, how do you compute that? Oh, different story, right? I hit the wrong. Man, okay, what did I just do? How you actually compute a scalar line integral? Well, there's details. You got to parameterize and pull back and details, right? But the big picture idea of a scalar line integral is that you're taking a curve, chopping it into little pieces, on which each of which the answer is simple, and then adding up. Okay, so the same basic idea works for surfaces. It's morally identical, right? We've got a surface. Oh no, we don't know how to do integrals on surfaces, right? However will we make sense out of a surface integral? Well, yeah, you're going to take your thing, you're going to chop it up into little pieces. Details to follow, right? Don't get lost in the details. But we're going to chop it up into little pieces. On each little piece, I'll go ahead and zoom in. On each little piece of surface, I mean, it's a little piece of area, and the total amount of stuff is stuff per unit area times area. Right? No crazy idea there. Stuff per unit area times area gives you stuff, and then you add that up to get the grand total amount of stuff. The same basic idea. Now, you do get a different construction because this is a different, let's see here, color choices. This is a different kind of a Riemann sum, so we're going to give it a different notation and a different name. But I think it's all pretty believable. It's pretty natural. And we're integrating over a surface, so we're going to call it a surface integral. Hard to see this coming, but there's going to be a different kind of surface integral that we'll need to distinguish. This has a scalar integrand and a scalar differential, so we're going to call it a scalar surface integral. Don't worry about what the alternative is. We'll get to that later, Wednesday. But so anyway, same basic idea, just sort of different details. Yeah.
How is this different from what we did in chapter 5 with like the pullback?
Yeah, no, it's very, very similar. Now, all the stuff we did in chapter 5 with pullbacks was change of variables, and that was what I'm going to call dimensionally the same. So we had two-dimensional region that we pulled back to a different two-dimensional region.
So now we're talking about like a three-dimensional.
Yeah. So here we have a two-dimensional thing in a three-dimensional world that we're going to pull back to a two-dimensional thing in a two-dimensional world. So the dimensions are just a little bit different, right? In chapter 5, it was always dimensionally convenient. Now we're, and by the way, that applies to both line integrals and surface integrals. With line integrals, it's a one-dimensional thing, but in a non-one-dimensional world, pulling back to a one-dimensional thing in a one-dimensional world.
Okay, and in chapter 5, it was keeping the same dimension.
Yeah, that's right. It was always two-dimensional thing in a two-dimensional world and pulling back to a two-dimensional thing in a two-dimensional world. Yeah. So just like we did back in chapter 6 with line integrals, pulling back through a parameterization, when we want to get around to actually computing a surface integral, we're going to pull back through a parameterization. And I think I'm out of time, so we'll pick up there next time. And see y'all later. Have a good one. Don't forget about attendance, and see you later.